In previous videos, we developed methods to find extrema of multivariable functions. This is what's called unconstrained optimization. We are just interested in what the function is doing naturally. A common situation in application problems is something called constrained optimization. To try to illustrate this to you, we'll just go through a simple example here. So a rectangular box with an open lid has to have a fixed volume of 4 cubic feet. What dimensions of the box are going to minimize the amount of material used? It's helpful to just view a picture of this. Now remember that this is a box that's supposed to be open on the top. If this is X and this is Y here and this is Z, the surface area of this box, the amount of material, is going to depend on the faces. 2 faces that are XY in area, 2 faces that are YZ in area, and then we'll have a single face that's XZ. This is the function that we're trying to optimize. However, there is an additional constraint. There's additional information that's forcing us to somehow restrict the values that we're interested in. And it has to do with the volume. This function of volume is x, y, z is equal to 4. We could try to solve this using the methods we developed before. And what that means is we can try to solve this constraint equation for one of the letters. So let's say we could solve it for z is 4 over xy, and then we could sub that into the optimization function. This function boils down to a new function of 2 letters. Everywhere I see a z, I would simply replace it with this 4 over xy. So we would have an 8 over x and a 4 over y. Now at this point, you can apply the techniques and the ideas from before on this new function a of x and y. Now, while that sounds great in principle, in general, we won't be able to isolate one variable from the constraint equation like this because it's probably going to be quite difficult to do it algebraically. In general, there is not really a hope that we're going to be able to solve our constraint function very easily. We need another approach. And this approach is more general, and in fact, it's going to use the implicit function theorem that we talked about in the previous video. We're going to let z equal f of x and y, and we're going to assume it's going to have partial derivatives that exist and are continuous, which means by a previous theorem it will be differentiable. So f is differentiable wherever this is true. In terms of a picture, we'll have the following. We'll have our function z of f, x, and y. This g of x, y equals k. This is going to be our constraint function. So we are going to let g have continuous partial derivatives, gx and gy, and we are going to assume that the gradient of g is never 0. This condition is going to ensure that one of either gx or gy doesn't equal 0. And that means that we can use the implicit function theorem. So when we talk about constrained optimization, we are interested only in the points on this function that lie right above that curve. And let's assume that our function has a maximum or a minimum right at some point x0 and y0. We are interested in what has to be true on the function right at that maximum point. So we'll assume that f is constrained to the points on this curve, g of x and y equals k in R2. So we're only going to be talking about the points right above that. We'll also assume that this point x0, y0 is an extremum of f. That means it's a high point or a low point. We're interested in figuring out what goes on at a high point or low point of the function. Because of these conditions right here, the implicit function theorem applies. So by our assumptions on g, this tells us that the implicit function theorem applies near this point x0, y0. Focus in on that point right there. If the implicit function theorem applies near x0 and y0, then what we have is y is a function of x and g as a function of x and y of x, and this is going to be true near x0 and y0. We have assumed that the gradient of that g curve isn't going to be 0 at any point along this curve. If gy happens to be 0 at that point, we'll just switch to gx and then apply the implicit function theorem there. So now what we can do is this implicit differentiation idea. The only difference here is that we have to use partial derivatives. So if we were to take the partial derivative of this curve right there, which now the implicit function theorem condition holds, the chain rule for multivariable functions tells me that this is going to be the partial of g with respect to x, the x derivative of x, the partial of g with respect to y, the y derivative of x, and this has to be 0. Now this is equal to 1, this is equal to y prime of x. I know that this exists by the implicit function theorem. The conditions that I imposed on g will ensure that it exists. Another way of writing this, gx, gy vector dotted with the vector 1 and y prime of x has to be 0. Now, by assumption, this vector is never going to be 0 at the point x0, y0. This is true in some small interval near x0, y0 by the implicit function theorem, but it's also true at that point. When I am near the point x0, y0, and this is the level curve of the function g, we can parameterize the curve with x as the parameter. X in the I direction and y of x in the j direction by the implicit function theorem. The derivative of this curve is then going to be 1i plus y prime of x j, and that's the result that I got right above. That is the tangent vector at this point. So this result right here is telling us something about the gradient and the tangent vector that we already know. The gradient g is orthogonal to r prime of x at that extreme point, x0, y0. This result's going to be important for us in just a moment, because now what we have to do is consider the values of f that are restricted to points satisfying this g of x, y equals k, the constraint equation, near our x0 and y0. Once again, the implicit function theorem says that wherever we see a y, we can write it as a y of x. So that means our function is really f of x and y of x, which is just a single variable function. It's just a function of this one variable. Now, since we have an extremum at x0 and y0, that means if we were to take the derivative of this expression, we know that it would have to be 0 or non-existent, but because our function f is differentiable, we know that the non-existence option won't work. So by the chain rule again, we will have the partial of f with respect to x, dx dx, plus partial with respect to y, dy dx, has to be 0. And just like before, we will have fx at the point x0, y0, fy at the point x0, y0, dotted with 1 y prime of x at that point is 0. The gradient of the function is also orthogonal to this tangent direction at the point x0, y0, or the gradient of that function is 0. So if we combine both of these results, at an extremum, both the gradient of the function, where it's been restricted to points on this curve g equals k, and the gradient of g are orthogonal to the direction of that curve. And that implies that both of these vectors are parallel, which implies then that they are scalar multiples of each other. And so this is a constant, and this is the key result that we've got right here. And this is what's called the method of Lagrange multipliers. That lambda is a scalar called the Lagrange multiplier. It's a new parameter that's been thrown into this problem. So if you want to just restate it, we're going to let f and g be functions of two variables defined on some common set D. If the function has an extremum at x naught, y naught, subject to this constraint, g of x and y equals some sort of k, and if the gradient of that function is never 0, then at that point, these two must be multiples of each other. Now, these are what are called necessary conditions at an extremum. If you know ahead of time that you have a maximum, then this must be true. It also applies to functions and constraints that have more than two variables as well. But when we solve problems, we're going to use this method in reverse. What we're going to do is solve a system where the gradient of our function equals this lambda gradient g, plus we have this constraint. This is going to give us points that are potential candidates for extrema. When you run this thing in reverse, there's no guarantee that the points you find are always going to be min or max. We don't know ahead of time if we have a max or min. So it's a typical math thing that we reverse the process to find potential candidates, and then you need other information to be able to find it. Really important. If this constraint equation, which is limiting the points we're going to search at, if this is a closed and bounded set in R2, then the extreme value theorem guarantees we have to have an absolute min and max. So then these points will be the right points. If you don't have a bounded constraint, then you need other arguments to be able to determine whether you really do have a min or a max. Geometrically, you can interpret the Lagrange multiplier method using level curves of the function f. Now, in terms of a picture, we've got our function living here. We've got a constraint equation somewhere over there. This result tells us that when you look at the different level curves of your function, the one where the two level curves intersect and they have the same tangent is exactly where you're going to have your max or min. When your gradients are parallel, that's when you're going to have it. If you look at these other places that aren't necessarily min or max, the gradient of one is not parallel to the gradient of the other. If this gradient vector on the constraint equation is 0, then you can have a problem. You could have a curve with the cusp, and then there's no tangent direction. So here is our first example. We're going to take a function which is a hyperbolic paraboloid, and we're going to subject it to this constraint where g of x and y is equal to this circle. So we would like to find the extrema of this f subject to this condition g equals 1. Now it's very simple here. What we need to do is find the gradient. So we'll get 2x negative 2y. We're going to get the gradient of g, 2x, 2y. And in both of these cases, f, g have continuous partial derivatives. You can just look at the components of these vectors and see that they are going to be defined everywhere. You will also see that the gradient of g equals 0 only when we're at the point 0, 0. But this point is not on the curve g is equal to 1. That point does not exist on the unit circle. So I'm going to satisfy the conditions. Now what we have to do is solve the system grad f equals lambda grad g and g equals 1. We have to solve this for the three variables, x, y, and lambda. Lambda is the Lagrange multiplier. It's some new artificial variable that we've created. So if I set equal the components here, I'll have 2x equals lambda 2x, negative 2y equals lambda 2y, x squared plus y squared is equal to 1. So this gives me a system that I can rewrite slightly. I'll have 2x into lambda minus 1 is 0. I'll have 2y into lambda plus 1 is 0. And again, I'll have the constraint equation, x squared plus y squared is equal to 1. So I'm going to number these equations. Unfortunately, when you have a system of nonlinear algebraic equations, there's no general way of solving them. You just have to do some combination of substitution and elimination. So from equation 1, I either have that x is 0 or lambda is equal to 1. If x is equal to 0, then equation 3 implies that y squared is 1 or y is plus or minus 1. So equation 2 will then tell me plus or minus 1, lambda plus 1 is equal to 0, lambda is equal to negative 1. So that means the potential candidates here are 0, 1, negative 1, and 0, negative 1, negative 1. Now, if lambda is equal to 1, if I put this into the second equation, I'll have y is 0. If I take that into equation 3, I will find that x squared is 1, so x is plus or minus 1. So the solutions here are going to be 1, 0, 1, or negative 1, 0, 1. And again, I'm treating these as x, y, and lambda. By the extreme value theorem, since my set of points that I'm considering is closed and bounded, I must have an absolute min and max for my function. So these candidate points, these 4 candidate points, some of them are going to give me the absolute min and max. The extreme value theorem and the nature of my constraint is guaranteeing that's going to happen. So now what we're going to do is check these xy points. And the options are 1, 0, negative 1, 0, 0, 1, 0, negative 1. I don't care about the lambdas here. I'm putting these values back into my function and seeing which is the largest, which is the smallest. Remember that my function was this hyperbolic paraboloid. F of 1 and 0, I'll get a 1. If I were to go negative 1, I'll also get a 1. If I were to go 0 and plus or minus 1, I'll get a negative 1. So that means I have absolute maxima at this point, and I have absolute minima at this point. So this curve is a saddle. And essentially what I've got is a circle. And if I constrain everything to lie on this circle, then I'm going to have some sort of curve on the surface of the function with some of these special constrained critical points. Some of them produce high points and some of them produce low points. If I were to look at the level curves of this particular graph, I would have my constraint equation that looks like this. So this is g equals 1. And you can take Maple or some other computer software to graph different level curves. So this green level curve here corresponds to the height of the function is 0. This dotted curve corresponds to the level curve where f is negative 1. And then this white curve corresponds to a level curve of the function where it's equal to positive 1. So at 1, 0, the gradient of my function was 2 and 0, and the gradient of my constraint equation was also 2 and 0. As advertised, these things are pointing in the same direction. So grad f and grad g are parallel. That's why that point turns out to be an absolute maximum. A similar thing happens over on the other side. Here, both of these things are negative 2 and 0, so they point parallel to each other. At the point 0, 1, the gradient of f is 0 and negative 2, but the gradient of g is 0 and positive 2. So they're pointing in opposite directions. However, they are still parallel, and this is what makes it an absolute minimum. So the method of Lagrange gives you a completely different way of locating absolute extrema of a function. There are extensions of this. You can apply this to multivariable functions of more than 2 variables. You can add more than one constraint, but they're all based on this fundamental derivation in this simplest case.